Hi everyone, this is Prof. K speaking. In this video, we're going to talk about collision theory, and then I'm also going to talk a tiny bit about transition state theory, which your book discusses but doesn't officially label as transition state theory. So the learning objectives for this video are to use the postulates of collision theory to explain the effects of the physical state, temperature, and concentration on reaction rates, and also to define the concepts of activation energies and what a transition state is, as well as learn about the Arrhenius equation and use it in calculations relating rate constants to temperature. So to start, we need to talk about what is collision theory and what are the postulates of collision theory. The first postulate of collision theory is that the rate of a reaction is proportional to the rate of reacting collisions. And so what this means is that if you have a bunch of chemicals in a beaker, the amount of times that a reaction will happen is based on how many times individual reactants run into each other. So if you think about this as an analogy that's not chemistry related, if you never encounter someone in your real life, if you never collide with anybody, maybe not officially, but like get in the same space as someone, if you never do that, then you're never going to form a friendship. And so if forming a friendship is the reaction rate, the more times that you run into someone, the more likely it is that you might befriend them. And so the same is true for chemical compounds. In order for a reaction to happen, the molecules need to run into each other. And the more that they run into each other, the more likely it is that a reaction is going to happen. The second postulate of collision theory is that the reacting species must combine or collide in the orientation that contacts the atoms that are going to be bonded in the product. So if you're trying to form CO2 from a carbon monoxide and an oxygen gas molecule, if the oxygens run into each other, they're not going to form CO2 and they're not going to bind to each other. If, however, the oxygen gas runs into the carbon with enough energy, then it could form CO2. And so your chemical compounds need to interact in a same orientation. And so the likelihood that they reach that orientation also affects the likelihood that you get a particular reaction. And the third postulate is that the collision has to occur with adequate energy so that they actually interact electronically and the electrons can rearrange and form the new bonds and the product. So in this example, where you have CO2 running into oxygen gas, they have to hit each other with enough energy that the carbon and the oxygens interact to the point where they can form the product. And when they're interacting and they're doing this like unstable distribution of electrons and they're trying to form this new shape, they form an unstable species called a transition state. And these transition states don't hang around for very long because they're just sort of the transition between a reactant and a product, which happens because the collision happens with enough energy. And so we haven't sort of described that too much so far when we talked about these reaction coordinates. But in this reaction coordinate, our reactants, when they collide, have to collide with enough energy that they pass through this unstable state that then falls to a product. And so the peak of these energy curves are our transition state. And our some geometry that's between your reactant and your product. And so the energy difference between the reactants and this high energy unstable transition state is what we're going to call activation energy. And so it is the minimum energy necessary in this collision between A and B, or between whatever, that will allow us to form a product during that collision between the reactants. And we're going to call this EA. And so I wanted to provide you an example of what a transition state could look like so that maybe you better understand what's happening here. So in a reaction with these SN2 reactants. This is an SN2 reaction. You don't need to know that. If you take organic chemistry, you'll learn more about this. But if this compound approaches this other compound where this yellow atom here can interact with the carbon in this compound, and if they collide with enough energy in the right orientation, then this intermediate unstable compound that doesn't look like any of the VSEPR geometries that we talked about last semester, because it isn't stable and it won't hang out here, forms where it's some geometry in between the reactant and product. And it has a high energy because it's unstable, and then it will quickly fall and form to the reactant where we've pushed this compound off of the carbon. And so we've replaced a functional group on this by traveling through this transition state. And so transition states have intermediate geometries where the electrons around all of these atoms are mixing together and interacting and trying to form some new bonds. And so postulate 3 is talking about sort of the disruption in the valence shell and how they're mixed together. And basically what that's saying is that the electrons around these compounds are mixing to form new bonds and break other bonds. And this is sort of what transition state theory is. And so this geometry is an intermediate geometry for this bond breaking reaction. And so we can use this activation energy in this previous plot to help us calculate interesting physical constants. And so the Arrhenius equation allows us to calculate the rate constant as a function of activation energy. So the rate constant that we've been using so far tells us sort of how quickly reactions happen in addition to sort of how much concentration we have. And so in this expression, what we're saying is that the rate constant is a function of this prefactor or frequency factor, which describes how often the molecules run into each other in the correct orientation. So it describes the likelihood of collisions and an exponential dependence on the activation energy. So if an activation energy is really high, then the minimum energy to do that reaction is high, and it makes it less likely that the reaction will proceed, so K will be smaller. If you have a higher temperature, then it reduces the sort of importance of activation energy, because that means that each individual molecule has more kinetic energy, because temperature is a measure of kinetic energy. So if you have higher kinetic energy in your system, it's more likely that the collisions will happen with enough energy to overcome the activation energy. So the rate constant sort of captures the different postulates into a form that allows us to numerically calculate constants from the energies of the system and the frequencies of which they're interacting with each other. And we also see this Arrhenius expression in some different forms because sometimes the data we're given makes it easier to solve this expression using a different form. So it might be the case that you're given some dependence on temperature that you can then use to calculate activation energies or the natural logs. And so if you look at this expression, it has the form of y equals mx plus b if y is the natural log of k, m is negative ea over r, x is 1 over t, and the natural log of a is b. So we could use this with data to tell us about the activation energy. We also can calculate how a rate constant changes if you change the temperature by dividing sort of one version of this at a particular point of temperature with another temperature. And so we can use both of these to solve problems and calculate some of these physical constants or the temperatures at which things happen. And the last thing that I want to show you is what's called the Boltzmann distribution. And so what this tells you is that if you are at a particular temperature, then the molecules that exist in your system can have a range of kinetic energy values. And if you have a low activation energy, then there's going to be more molecules that have enough energy to overcome the activation energy and to do the reaction. And so by increasing the temperature of your system, it's possible to make it so that more molecules are able to overcome the activation energy. And so we can relate this back to the postulates of the collision theory, which say that if you give the system more kinetic energy, then the collisions are going to happen with more energy. They're probably going to happen more frequently, and hopefully in those happenings, they'll happen more at the right orientation. So you're providing the system with more opportunities to overcome the activation energy and move to the final product. And so this is sort of a visual representation of how changing the temperature affects how many molecules in a particular system can undergo the reaction that you're interested in.